Hello, Professor. Can we start?
Yes.
Let me introduce you to the audience, and then I will hand over the session so you can carry on. Can start the talk. Thank you, Professor. Good evening, everyone. Welcome to the Network Seminar Series hosted by the Center for Networked Intelligence at the ECE and RBCCPS IISc. It's my pleasure to introduce today's speaker, Professor Vishal Shrivastav. He will be speaking on enabling and exploiting high speed in network computing. Vishal Shrivastav is an assistant professor in the School of Electrical and Computer Engineering at Purdue University. His research interests are broadly in computer networking and systems, with a focus on programmable and reconfigurable networks in network computing and network hardware design. Vishal received his PhD and MS degrees in computer science from Cornell University and his undergrad degree in computer science and engineering from Indian Institute of Technology, Kharagpur. Vishal is a recipient of a National Science Foundation Career Award, a Google Research Scholar Award, a Cisco Research Award, and a Eta Kappa Nu HKN Outstanding Professor Award. We request the audience to keep your microphones on silent for the duration of the talk. You can post your questions in the chat box, which will be addressed by the speaker during the Q&A session. Over to you, Professor.
All right. Thank you so much for the introduction. So my talk is going to be all about in-network computing, how we enable it, and more importantly, how we exploit it to build high-speed distributed and network applications. Now, before I go into in-network computing, I want to start by first briefly discussing traditional distributed computing architecture, just to put things into perspective. So if you think about traditional distributed computing, in that the computation is typically distributed across multiple nodes, and then the entire network is kind of abstracted as a pipe, whose sole job is really to just carry messages between these end hosts. So in other words, network is a real passive partner in communication in traditional distributed computing. Now, in-network computing changes that entire paradigm by making network an active partner in communication. So the idea behind in-network computing is that not just the end hosts where we can do the computation, but we can also run custom computations on network devices, such as network switches. And now when a packet goes through the network, then each switch can perform custom computations on top of that packet, update its local state, and even update the state within the packet before forwarding the packet to the next switch, which can do its own custom computations, and forward it to the next switch, which can do its own custom computations until the packet finally reaches the end host. Now, at this point, a natural question might be that what is it that we gain with in-network computing that is hard to achieve with the traditional end-to-end distributed computing? And the things that we gain are twofold. So first, we observe that switches sit at a very different vantage point in the network compared to the end hosts. So if you think about the end hosts can only see traffic going in and out from a particular end host. Whereas switches, since they connect multiple end hosts together, have a more central vantage point. So they can see traffic between multiple end hosts at the same time, which makes them much better suited to run certain specific kinds of computations. For example, partition aggregate computations, or caching, or load balancing, and so on. And if we are indeed able to implement these specific computations on switches, there are some gains to be had. For example, these computations can significantly reduce the network tripling for certain computations. As an example, consider a distributed key value store, which is the core for most deployed distributed services in the real world. So in this try example, let's suppose that node A wants to retrieve a key value object from node B with key 10 and value 2000. So if you wanted to implement it using traditional distributed computing, it would take you 8 hops to fetch the data. However, if you had this ability to do caching inside the network, then this network trip length can be reduced to as low as just 2 hops. In-network computing can also help you save network bandwidth. So here is another very important application in today's world, which is gradient aggregation for ML training. So in gradient aggregation, there are many different workers who generate their own gradients, and then they typically send these gradients to a parameter server that aggregates those gradients together and does some computation on top of the aggregated gradient. So that's how a lot of ML training happens. So again, if you are using a distributed computing architecture, then if you notice, the dashed blue link in this example will carry 2 packets. However, if you had the ability to do in-network aggregation, where you could aggregate these values inside a switch itself, then the amount of, or at least in this example, the number of packets going over these blue links reduces from 2 to 1. In this way, you can save bandwidth. And you can imagine that if you scale it out to a larger network, these bandwidth savings are going to get more and more significant. And finally, switches by design run at line rate. And by line rate, I mean multiple terabits per second for state-of-the-art switches. Now, if you compare it to your typical CPU-based servers, then the processing throughput for these switches is orders of magnitude higher than the CPU-based servers. And not just that, the latency of computation in these switches is also orders of magnitude lower than in these CPU-based servers, and also deterministic. And all this comes at a much better power efficiency than you can get if you use purely CPU-based servers. So this kind of motivates us further to offload some of these computations from these servers to the switches to improve the overall system. So given all these benefits that one can have through in-network computing, next I'm going to discuss the technology that makes it all possible. And that technology we call programmable switches, which are now available, commercially available by most switching vendors around the globe. So if you open one of these programmable switches, what you will find inside is, well, first you will find a very low-end CPU and some memory, which is typically used to implement control plane operations, which is the same for pretty much any switch, programmable or not. But the real key sauce, which separates these programmable switches from your traditional fixed function switches, is in the data plane. Because in the data plane, these programmable switches have this programmable switching chip, which can process packets at multi-terabits per second, just like traditional fixed function switches. But unlike these traditional fixed function switches, you can actually program this switching chip with custom packet processing programs using some domain-specific language. Most popular of them is called P4. So what does the architecture of this programmable switching chip look like? So it looks something like this. So most programmable switching chips implement some version of this very popular processing architecture called reconfigurable match table, or RMT architecture. So within this RMT architecture, you have multiple components. So at the very start, you have what we call a programmable parser. So as the packet comes in, it goes through this programmable parser, and you have the ability to program this parser to parse any custom header fields of your choice. So once the packet goes through this programmable parser, it goes through a series of what we call match action stages. So in each of these stages, you have many different components. So for example, you have multiple match action tables, which can be either implemented using SRAM if you want to implement exact match, or they can be implemented using TCAM if you want to do ternary match. And again, you have the ability to program these tables to match on custom header fields and take custom actions. Besides, each stage also has some switch registers, again implemented using SRAM, which you can use to store custom state in the switch. And then finally, you have ALUs in each of these stages, multiple of them actually, to perform custom ALU operations. And these ALUs can be classified into 2 classes. Either you can have stateless ALUs or stateful ALUs. So stateless ALUs perform operations only on the packet header fields, whereas the stateful ALUs can perform operations both on packet header fields and switch registers. So that's how we distinguish between the two of them. And finally, once the packet has gone through all these batch action stages and all the processing has happened, then you typically put this packet in one of the output queues, and then a scheduler schedules this packet out on the output link. So this is what a typical programmable switch architecture looks like. And turns out that this architecture is quite powerful in the sense that people have shown that you can use this programmable switch architecture to improve the performance of many key distributed and network applications, including things like congestion control, load balancing, distributed key value store, even consensus protocols, ML training, and so on and so forth. Now, as great as these programmable switches are, as powerful as they are still far from perfect. And the limitation of these programmable switches really stems from the fact that the RMP architecture that I just described is a domain-specific architecture. It's not general purpose in the sense that you cannot implement any arbitrary algorithm on top of these switches. And this is really by design. See, the first order objective of any switch is to be able to process packets at line rate. That's always going to be the first order objective for any switch, including a programmable switch. So programmable switches end up sacrificing generality for line rate processing. And on top of that, these switches also have several practical constraints like, power, chip area, cost constraints, and so on and so forth. So what all this means is that the compute and the resources on these switches are typically quite constrained. For example, these switches have limited number of switch registers to store custom state. They also have a limited number of match action stages, and also the number of stateful ALUs per stage is also very limited. Further, the ALUs that I told you about, they are very simple ALUs in the sense that they can only perform very simple operations like additions, bit shifts, comparisons, so on and so forth. They can't even perform operations like multiplication and division. Again, because you have to hit line rate, and those operations just don't enable you to hit line rate. So given all of these restrictions, it kind of becomes really challenging if you're trying to implement applications or operations that tend to be either compute or state intensive or both, right? So to illustrate this point, I'm going to take an example of a specific network application, namely network intrusion detection, which is a very, very important network application deployed in pretty much all real-world networks to protect us from malicious traffic. So what does a network intrusion detection system, or NIDS, does? Well, the job of NIDS is to analyze the traffic that is going through the network and classify that traffic as either being malicious or benign. And if it is indeed malicious, then you take some action. So if you look at traditional NIDS, traditionally NIDS used to be rule-based. For example, SNOT is a very popular example of NIDS, of a rule-based NIDS. So what is a rule-based NIDS? So here, a rule is simply a set of predicates defined on top of packet header fields and payload contents. For example, a sample rule could be that if the destination port of the packet is 80 and the payload of the packet contains some regular expression, then classify it as malicious traffic. So that's how rule-based NIDS works. Now, there are some fundamental limitations to rule-based NIDS. For example, they cannot do behavioral analysis of traffic. That's just not possible, which means that it cannot detect complex malicious patterns in traffic. Further, rule-based NIDS relies a lot on payload inspection, which is really not possible if your traffic is encrypted, which is really most of the traffic over the internet these days. So given these limitations of traditional NIDS, more recently, people have started to explore ML-based NIDS. So here, the idea is that as the traffic is going through the network, you extract packet and flow level features from the network traffic, examples of which I will show later. But the important thing is that to extract these features, you typically don't rely on payload. Most of these features can be extracted by just inspecting the header, which is typically not encrypted. And once you have extracted these features, you feed it to an ML classifier, which by design is trained to detect complex malicious patterns in traffic, and then you have just a better NITs. So if you look at the workflow of an ML-based NITs, it looks something like this. So a packet comes in. The next thing that you do is you extract packet level features from this packet. So these are things like your source IP, destination port, so on and so forth, that you can extract from the packet header. Then you also extract and update flow level features. So these features span across packets. So things like mean packet size of a flow, inter-packet arrival time in a flow, so on and so forth. So you extract these features as well. And once you have extracted these features, you feed them to a ML classifier. And then that ML classifier will classify the packet as whether it's malicious or not. So that's the typical workflow of ML-based NITs. Now, existing ML-based NITs are typically implemented on a server cluster. So the way it works is that as the traffic is going through the network, you take a tab of that live traffic and send it to this remote cluster of servers where you have implemented your ML-based NITs. And then these servers will analyze the traffic. And once they have analyzed the traffic, they will classify it as either malicious or benign. And if it is malicious, then they will return back to the switches and install some rules on the switches to react to that malicious traffic. For example, block it or drop it, and so on and so forth. So that's how existing ML-based NITs are implemented. Now, there are some obvious issues with it, right? So for example, you need a dedicated server cluster to just implement network intrusion detection. So this has high cost, management, so on and so forth. But more importantly, this architecture also results in this large feedback latency. Because first you have to send the traffic to those remote servers, then they will do their analysis, and then the rules are installed back in the switches. So that's a pretty large latency, which limits your ability to react to malicious traffic in a timely manner. So a promising alternative to this architecture is to implement the NITs in line with the network traffic on the programmable switch itself, if you have access to programmable switches in your network. Because if you do that, then the benefits are quite obvious. Because now you don't need to have a dedicated infrastructure for NITs, but more importantly, now you can inspect every packet going through the network at line rate and detect and react to malicious traffic in real time. So that really improves the efficiency of your network intrusion detection system. So given this, the question is, how do you go about implementing this entire pipeline on a programmable switch? And for that, we can break this pipeline into separate components. So in this case, we have broken it down into 3 different components. So let's start with the first component, which is extracting packet level features. So it turns out this is pretty straightforward using a programmable parser. So you can program your parser to extract whatever features you want to extract from the packets. The next component is about storing and updating flow level features. So there you need some memory to store these features, and for that, programmable switches do have SRAM registers that I talked about earlier, where you can store custom state. So you can use that to store flow level features. And finally, you have to somehow implement an ML classifier on the switches. And again, like I said, you do have access to ALUs on the switches, and which you can potentially use to implement some form of ML classifier. Now, like I said, extracting features using programmable parser, that's the easy part. You can easily do it. However, implementing the other 2 components is not as easy. In fact, it's quite challenging given the constraints of programmable switches that I talked about earlier. For example, the number of SRAM registers on the switches are, again, very limited, only a few megabytes. But if you think about these switches, especially in the data center context, they can carry millions of flows at any given time. And if you are indeed storing this per flow state in the switches, you will need somewhere between 50 to 100 megabytes of memory. Similarly, If you want to implement ML classifiers using ALUs, you have to take into account that the number of ALUs, especially the stateful ALUs, is very, very limited on these switches. And like I already said, they can only perform very simple ALU operations. So nothing like a matrix multiplication or anything like that. That's like completely beyond the scope of the switches. And they also have limited number of pipeline stages. So this means that if you are trying to implement an iterative algorithm, then you can only have so many iterations as the number of pipeline stages and not beyond that. So these are all the limitations that you have to overcome if you want to indeed implement an application like network intrusion detection, which is simultaneously state intensive as well as compute intensive. So what I'm going to do next is I'm going to go through each of these challenges one by one and present two systems that we have developed over the course of past few years that tries to overcome these challenges, both in the context of network intrusion detection, but also in a more general context. So let's start with the first challenge. How do you deal with state-intensive network applications, given that you only have very limited memory on these programmable switches? Now, the classic solution to these problems is you essentially store all your state on some off-chip memory, which is going to be larger, but also slower, right? So for example, like I mentioned earlier, these programmable switches do have a control plane where you do have some amount of DRAM available, which is going to be of the orders of gigabytes. So you can use that DRAM to store state. And then the performance of your whole pipeline would simply boil down to how efficient your caching algorithm is between the DRAM and the SRAM. So the problem really boils down to designing efficient caching between SRAM and DRAM for state-intensive network applications to get around this limitation of programmable switches. Now, caching is an age-old problem. We all know that, right? And there are several online caching heuristics that are used in practice, LRU, LFU, so on and so forth. However, it is also pretty well documented that all of these caching heuristics fall significantly short of the optimal offline caching algorithm, which is the Palladi's algorithm. And if you ask what is the fundamental reason for this performance gap, well, the fundamental reason for this performance gap is that the offline algorithm, which is the Palladi algorithm, uses the knowledge of future state accesses to make optimal decisions. However, in an online system, you just don't have access to future state accesses. And hence, this limits your ability to make optimal caching decisions. So this really prompted us to ask the following question. So while it might be hard to implement this future-aware online caching in a general setting, the question that we ask is that is it possible to do it in a network setting? And especially for the kind of network applications we are interested in offloading to these programmable switches or in network computing. And turns out that it is actually possible. At the very least, you can provide some partial visibility into future state accesses in a network setting. And for that, we built a system called SEER, which was published just last year. And SEER is really based on two key insights. So the first insight that SEER uses is that in case of network applications, the state accesses are much, much simpler than for general computations. For example, in case of network applications, the state accesses are often triggered by incoming packets, and the state is often indexed by some packet header fields. So for example, if you talk about NIDs, so in case of NIDs, as the packet comes in, typically what we do is we extract the 5 tuple from the packet. So this essentially identifies a unique flow. And then you typically take a hash of that 5 tuple that gives you the state index. And then you can use that index into your flow feature table. So this is an example of NIDs, but turns out a lot of network applications follow a very similar pipeline. So to summarize here, the insight that we draw here is that the state access index for network applications are carried in incoming packet headers, and they can be encoded using a very small number of bits. So that's the first insight. Now, the second more important insight that we use is the fact that packets, as they go through the network, they experience various kinds of delays. For example, queuing delay, transmission delay, propagation delay, so on and so forth. So let's consider this twice example, and let's consider the fourth packet that is sitting in the queue here. Now, this packet is going to arrive at the target node where we are implementing caching after it has suffered the queuing delay, transmission delay, propagation delay, so on and so forth. So traditionally, these delays are considered bad in a network context because they increase the latency of the packet. But turns out in our context, they can be leveraged to do something useful. Because while these packets are waiting in the queues to be transmitted, what we can do is we can extract the state index from these packets and send it to the target node in advance so that the target node knows in advance what future packets or what future states will be accessed. And based on that, it can make smarter caching decisions. So that is our second key insight, that delays in the network can be leveraged to forward state index information in advance. So based on these two insights, we built the entire system called SEER. However, if you really want to implement these two insights in practice, there are some challenges that you need to overcome. So the first challenge is, how do you forward these future state access indices in a timely manner and also at low bandwidth overhead? And the second challenge is that once a target node has received these future state access information, how do you use it to make smarter cache prefetching and eviction decisions? So next, I'm going to describe how we handle these two challenges one by one. So let's talk about how do we transfer this, or rather exchange these state index information between different nodes. So for that, every switch in the network maintains a metadata that we call a future packet metadata for every queued packet. And this future packet metadata stores two things. The first thing that it stores is the state access index that the packet is carrying. So for example, hash of 5 tuple. And it also stores the future time at which this packet will arrive at the next hop. And for that, SEER only exchanges these FPMs between directly connected nodes, because in that case, you can have this very accurate estimation of when this packet is going to arrive at the next hop. So given these FPMs, the next question is, how can you exchange these FPMs in a very efficient manner, which is to say that you are able to exchange them as soon as possible while incurring very low bandwidth overhead. So there are many options to do that. So here is the first option. What you can do is you can create a control packet for each of these FPMs and then send them to the target node in advance. Now, the only issue here is that Ethernet packets are typically at least 64 bytes in size, while these FPMs can be much, much smaller in size. So if you do go this route, then you might end up wasting a lot of bandwidth, which is really not good. Now, the obvious way to get around this issue is to batch things together. So you can batch multiple FPMs into a single control packet and then send that packet out. Now, this would work very well if you have a lot of FPMs to send at any given time. However, if you don't, then you have to wait. You have to wait for the batch to be full, but you really don't know how long you have to wait because you don't know what packets are going to arrive in the future. So this can result in this non-deterministic batching latency, which means that you are not able to forward these FPMs in a timely manner to the target node. Ideally, you want to forward them as soon as possible so that the target node has the largest degree of visibility into the future state access. So in SEER, what we try to do is we try to get the best of both worlds. So we try to make sure that you are able to send these FPMs as soon as possible, but also making sure that it doesn't result in high bandwidth usage. And to achieve this, the insight that SEER leverages is to send these packets, or rather FPMs, in inter-packet gap. So if you recall from your introductory to network class, the Ethernet rather mandates that between any two Ethernet frames, there should be a minimum of at least 96 bits of inter-packet gap. And by default, this gap is just filled with zeros. So our insight is to leverage this and repurpose IPG by rewriting these zeros with our FPMs so that we are able to send it with zero bandwidth overhead. So the idea is as follows. So Seer sets a configurable batch parameter n, and if the number of FPMs is less than n, Seer sends them using these IPGs without incurring any bandwidth overhead. However, like I already mentioned, these IPGs are limited in size. So in the worst case, you are only going to get 96 bits. So you're not able to batch a lot of FPMs in a single IPG. So if you have indeed a lot of FPMs at your disposal, the better thing to do would be to just batch them in a single control packet and send it out. But now you don't incur the batching latency that you had to incur in the previous case, because batching only happens when the number of queued FPMs has exceeded the value of m. Otherwise, we send them using IPGs. And this is how Seer gets the best of both worlds. It's able to send these FPMs as soon as possible, while also incurring zero bandwidth, or rather low bandwidth overhead and low latency overhead. So that's the first idea behind Seer. Now, once you have these FPMs received at the target node that is performing caching, the second question is, how do you use those FPMs to do a smarter prefetching and cache eviction? So let's start with prefetching. So the goal of prefetching is to fetch state in order of predicted time of access. That's the goal of any prefetching algorithm. And this becomes really, really simple in Seer, because all you really need to do in Seer is simply sort the received FPMs in increasing order of the future time of arrival of the packet corresponding to each FPM. So this information is already carried in each of these FPMs. So all you do is you simply sort these received FPMs in the order of future packet time arrival, and then you prefetch the packets or the state in that same order. So in this example, you would prefetch state as 0, then you would prefetch state as 3. You don't need to prefetch state as 7 because it's already in the cache, at least in this example. And then finally, you prefetch state as 5. So that is going to be your prefetch order. So that's how prefetching happens in Seer. But what about cache eviction? So for cache eviction, our goal is to emulate Baladi as closely as possible, because that is the optimal algorithm. So if you again remember what Baladi's algorithm does, Baladi's algorithm does is it evicts the state that will be accessed farthest in the future. That's the idea behind this optimal offline algorithm. So we try to emulate the same algorithm within Seer. However, the challenge in Seer is that you don't have access to the entire future. You only have access to partial future state accesses. So what do we do in that case is we split the cache state, the current cache state, into two logical sets. So the first set is going to contain all the states within the cache for which we know the future access time, which is to say that for those states, we have received the FPMs. And then the second set contains all the cache entries for which we don't know what is the future access time. So that's how we split the cache. And once we have split the cache into these two sets, what we do is we prioritize evicting states from the set that contains unknown future access times. The rationale behind that is that it is likely that those states will be accessed later than the states for which we already know the future access time, because these packets are definitely queued at the previous hop. That's how we receive the FPMs. So we know for sure that these states are going to be accessed very soon in the future, whereas for those we don't know the future access time, they are likely to be accessed farther in the future. So just following Baladi, we prioritize evicting states with unknown future access time. And to do that, you can actually use any caching heuristic of your choice. So you can use any state-of-the-art caching heuristic to do the eviction from this unknown set. Now, this also means that the worst case performance of SEER simply reduces to the performance of whatever caching heuristic that you have chosen. However, in the best case, where all states in the cache have known future access time, you can implement Baladi accurately. You simply evict the state that will be accessed farthest in the future, which means that in the best case, SEER reduces to Baladi. So the takeaway from this slide is that the performance of SEER is really bounded between the state-of-the-art caching heuristics that we use in practice today and Baladi. And turns out in practice, the performance of SEER is actually much closer to Baladi than the caching heuristics. So here is an experiment to illustrate that. So in this experiment, we ran, or rather we implemented 2 in-network applications in a simulated network environment. And then we used many, many different caching algorithms to see the performance. So here the performance is measured in terms of cache-miss ratios, so lower is better. So as you can see from this graph, SEER achieves 60 to 180% lower cache-miss ratio than several state-of-the-art caching heuristics like LRU, LFU, R, S3, FICO, C, and so on. And not just that, SEER's performance is within 50% or 15% of Baladi, which is the optimal algorithm. So this is really the benefit of having that partial visibility into the future state accesses. Okay. So that is about SEER and how SEER solves this problem of implementing these state-intensive applications on network devices such as programmable switches. So the next thing that I'm going to focus on is how do you implement compute-intensive computations, such as an ML classifier on these programmable switches, given the constraints of limited number of ALUs, simple ALU ops, limited number of pipeline stages, so on and so forth. So here what we try to do is we try to build an efficient compute utilization and multiplexing techniques to work around these compute limitations of the programmable switches to implement compute-intensive applications such as an ML classifier. So for that, I'm going to talk about a specific system that we built called Leo. So Leo focuses on implementing decision tree-based ML classifiers. Now, why decision tree? Well, because decision trees are much more easily interpretable than your black box neural networks, which is really liked by network operators to be able to interpret and figure out if something goes wrong, why it went wrong. Further, it has been shown that at least for the network intrusion detection application, decision tree performance is competitive with deep neural networks. And finally, if you know about decision trees, you know that the ALU operations required to implement decision trees are actually very, very simple. It's mostly just comparison operations that you do, which is supported by programmable switch, unlike DNNs for which you might need matrix multiplication and things like that, which is, again, very hard to implement on programmable switches. So because of all these varied reasons, Leo focuses on these decision tree-based ML classifiers. However, turns out that even implementing a decision tree is not that trivial. So for example, if you just do a naive mapping of a decision tree on to a programmable switch, you can do something like this. You can implement each level of the tree in one of the pipeline stages on the switch, and you can use the ALUs to implement each node in the tree. Now, this looks fine in theory, but in practice, this is not really feasible for a couple of reasons. Well, first of all, your stateful ALUs are really, really scarce. So as your tree size grows, you will just run out of these stateful ALUs. And similarly, the number of pipeline stages is also limited. So again, if your tree is really large, you are just going to run out of number of these stages. So essentially what this means is that these limitations fundamentally limit what size of decision tree you can support on these programmable switches. And this really begs the question that is there a better way to utilize these available resources so that we are able to support larger and larger decision trees, which hopefully will give us better classification accuracy. So for this, we use two key ideas. So here is the first idea. So we observed that at runtime, no matter what decision tree you have, at runtime, only one node per level is going to be accessed, no matter how big your tree is. Right? That's how decision trees work. So what this means is it gives us an opportunity to allocate resources for only one node per level, provided that you have a very nice multiplexing technique to multiplex between all the nodes within the same level at runtime. So assuming that you have some form of multiplexing going on, you can get away with just a single ALU per stage to implement the entire decision tree. So this can give you a lot of compute efficiency. So here is an example. So suppose you have this decision tree with 3 levels and then the leaves at the end. So you can implement this tree using just 3 ALUs, 1 ALU per stage, rather than using 1, 2, 3, 4, 5, 6, 7 ALUs in the naive case. So it reduces the number of ALUs from 7 to 3. Now, obviously, you have to be able to multiplex between all the nodes within the same level at runtime. And turns out multiplexing these nodes is also very easy because all you really need for that is the output of the previous stage to figure out which node to choose in the next stage. For example, the output of the root node will tell us whether we should choose the left child or the right child in the next stage, and so on. So that's how you can implement the entire tree in a very efficient manner on these programmable switches. Now, one question that you might have here is that even though we have reduced the number of ALUs, now we have introduced these extra components, the multiplexers, right? So is it the case that we are just trading off one devil for another? Well, not quite, because turns out these multiplexers can be very efficiently implemented using very small amount of SRAM memory, which is available on these switches. So it's really not that big of an issue, whereas the stateful ALUs, they are the ones that are scarce on the switches, and that's the limiting resource here. So that's the first idea. Now, this idea is not perfect. Even though it reduces the number of ALUs needed, what it doesn't help us with is increasing the depth of the decision tree, because the depth is still limited by the number of switch stages, even with node multiplexing. Right? So this means that if a switch has d maximum stages, the largest tree that you can support can have a depth of at most d. So the next question that we ask is there a way to scale the tree depth as well? And for that, we use this idea of subtree flattening and multiplexing. So what is this? So here what we do is we try to identify common subtree structures within a decision tree. So in the example shown here, we have identified 2 common subtree structures. And then the idea is that instead of implementing these subtrees like before, where you implement one level of the subtree in every pipeline stage, we employ a different implementation strategy, which is to flatten the entire subtree in a single stage. And we can do this by leveraging the insight that you can actually represent a decision tree, any decision tree, using a single Boolean truth table. So for example, if you consider the left subtree here, you can implement it using the Boolean table shown on the right. So here, all we have to do now is compute the value of each of these nodes in parallel so that we can do, in the best case, in a single stage. And once we have these outputs, we can use those outputs to index into this decision tree truth table to get the final result. So that's the idea. And just to complete the story, you can also multiplex multiple of these subtree structures depending upon the output of the previous stage. For example, here you can multiplex the left subtree and the right subtree depending upon the output from the root node a less than 0. So just by doing all of this, we have reduced the number of stages needed to implement this depth for tree using just 3 stages instead of 4. And as the tree size increases, these benefits become more and more exacerbated. Now, a natural question at this point might be that, well, if this is really an option of flattening the entire tree in a single stage, why don't we just flatten the whole tree? Why are we focusing only on subtrees? Right? That's a natural question that one could have. Well, the reason that we are not flattening the entire tree, but rather trying to figure out these subtrees to flatten is again because of some practical constraints that you have on these switches. For example, like I have already mentioned, the number of stateful ALUs per stage are limited on the switches. So when you are computing the value of each node in parallel, you can only compute so many nodes per stage. So for example, if your number of stateful ALUs per stage is 4, you can only compute the value of 4 nodes in a given stage. So if the number of nodes is large, you are just going to consume a lot of stages just to compute the output of each node. So that kind of beats the purpose. Second issue, again, is that the table size also grows exponentially with tree size. So if your tree is really, really long, then obviously the table size would also increase, and then that also means that you will now need multiple of these match action stages to implement the entire table. So really, the key here is that we have to be able to find these optimal subtree structures to maximally utilize the resource. So this is a very fine balancing act that Leo needs to play, given the resource constraint on the switches and given the sorry. Sorry about that. Seems like there is some alert going on at Purdue. Right. So what I was getting at is that Leo really has to do this balancing act between these, between choosing what should be the right subtree size so that we are indeed able to utilize the resources efficiently and support large and large decision trees. And in fact, turns out that if you are indeed able to support these large trees, you do get benefits in terms of classification accuracy. So here is a graph where we implemented Leo and several other baselines using 2 intrusion detection datasets, PIC IDS 2017 and UNSW NV15. And what you can see here is, at least for one of these datasets, which is CIC IDS 2017, Leo achieves much, much better performance than other state-of-the-art programmable switch-based decision tree implementations like LC, pForest, and switch tree. And again, the reason for that is Leo is able to support much larger trees than those other baseline solutions because of this efficient resource multiplexing that Leo is doing. Further, we also implemented the decision tree on a control plane where you have a general purpose CPU, so you don't have any resource constraint and you can build as large a decision tree as you want. So there you build the optimal size decision tree and see what accuracy you get. And turns out that Leo's accuracy is actually quite close to even this optimally sized decision tree while being able to process data at orders of magnitude higher throughput than the CPU-based solution. So this way you get the best of both worlds. You are able to achieve high classification accuracy while also being able to process packets at line rate. So to conclude, in-network computing presents this new paradigm for distributed computing that has this potential to improve the performance of many distributed systems and network applications. However, the key challenge lies in the domain-specific processing of programmable network devices. Now, some might see this as a limiting factor, while others might see it as an opportunity for research. And here are 2 broad research directions that I have outlined here. So the first research direction is more hardware focused, where you can try to improve the capability of these programmable network devices. Seer was an example of that, where we tried to improve the caching subsystem on these programmable network devices to support state-intensive network applications. But then there are other opportunities as well. For example, you may be able to design richer compute units, improved ways of sharing state between these multiple pipeline stages, how to do processing across multiple pipelines, and so on and so forth. So there is a lot of opportunity in that space. The second opportunity is more from the algorithmic and system standpoint. So here what we assume that we have the programmable switch hardware as it is with all its limitations, and instead of trying to overcome those limitations using hardware innovations, what we try to do is we try to overcome those limitations by building smarter algorithms and systems on top. So Leo was an example of that, right? Where we worked with the limitations of the programmable switch, but we came up with this really nice multiplexing technique for this decision tree based classifier. So based on your use case, you can also come up with, say things like approximate algorithms or computations or distributed multi-switch computations. Or you can even think about dividing the labor between switches, network interface cards, and hosts, and so on and so forth. So overall, even though there has been a lot of progress made in the last decade in the space of network computing, turns out there is still a lot that remains to be done, which makes it really, really exciting from research perspective. So on that note, I would like to thank everyone for listening, and I'm happy to take any questions.
Thank you very much, Professor, for giving such a wonderful talk. So I request the audience to ask questions. You can either ask or type them in the chat box so that I can relay your questions. Yes, Professor, please unmute yourself. Hello.
Yes. Hello.
Sorry.
I'm not able to hear the question.
Professor, we are unable to hear you.
You're audible. Hello, am I audible now?
Yes.
Yeah. So I'm saying Joy only. So in your first first of all, thanks for the great talk. Your
Thank you.
first piece of work, you added your FPMs to the IPGs, right?
Yes.
Using P4. But
no, not using P4. So that's not possible in P4. So we had to modify the physical layer of the switch to do that.
Oh, okay. So your switch gives you that ability.
Yes, our implementation gives us that ability. So we implemented an FPGA-based switch to show that this is indeed possible. So all you will have to do is just modify the physical layer of whatever network device that you're working with to make this possible.
Okay. Thank you. Yeah, that was my question. Thank you.
Yeah, I had a question. This is Preetam Patel from CNA. So, what part of this can be extended to the host side, like at the SmartNIC or a DPU, more than the SmartNIC?
That is a very good question. So just think about this network intrusion detection problem, right? So at least in Leo, we focused on implementing this entirely on these switches. But you can very well think of distributing this between switches and SmartNICs. In fact, this is something that we are looking at currently, because if you have a SmartNIC, then you can do much more compute-intensive operations. For example, you can do regular expressions and things like that to payload inspection, which you can't do on the switches. So you can think of a whole ecosystem where you have these different programmable network devices and even end-host CPUs, and think about how can I distribute the labor between these different devices taking into account what are the advantages of one device over the other. For example, a programmable switch might be very good at handling these header level features and so on and so forth, whereas a SmartNIC would be better at doing these regular expressions or implementing these regular expressions and things like that. So maybe that could be one way of dividing the labor between the two.
So, have you explored the parsing or offloading the parsing part to the SmartNICs or DPUs and actual classification based on just some tags in the header to the switches? Because the switches are where you can aggregate flows from multiple sources, right?
Right. Yeah, so that is a very valid point. So one architecture could have been that you use the switches to only extract the features, and then you actually implement this ML classifier somewhere on say a smart NIC where you can implement even bigger classifiers like DNNs and so on. You don't have to restrict yourself to decision trees. So that is a very valid architecture where you extract the features of the switches, send it to the end host, and then it does the analysis. However, like I mentioned earlier, that this does have that feedback latency associated with it. So the benefit of doing everything on the programmable switch is that you can react to these malicious traffic pretty much at packet level time scale on per packet basis. However, if you have to transfer these information to some remote server or a smart NIC or whatnot, then there is going to be some inherent latency associated with it, which means that you won't be able to react on a per packet basis at the very least. So that's the trade-off that you have to play with.
Okay, thank you.
Yeah.
So one more question, Professor, from the chat box.
Yes.
So they're asking, like, how do you program the control plane?
Sorry?
So they are requesting, like, how do you program the control plane?
How do you program the control plane? So the control plane is really just running a simple, something like a CPU, right? So that's the architecture. So you can program it using any high-level language like Python and so on. So that's a very well-studied area, especially in the context of software-defined networking. You have a lot of control plane implementations out there, like POX, NOx, so on and so forth. So that is just implemented using your regular programming language because it's implemented on top of CPUs. It's the data plane for which you need these domain-specific languages like E4 and so on, because that's not general purpose.
Okay. Thank you, Professor. Any more questions? So I think, Professor, you have addressed almost all the questions. So let us conclude the session for today. Thank you once again, Professor, for
of course. Yeah, thank you for inviting me. It was great.
It's a pleasure hosting you. Thank you so much. And audience, thank you very much for attending this talk. We hope you have a great evening. Thank you, everyone.
Thank you.
Rest of the questions.